Good morning to everyone, and welcome to the Open University. I'm Michael Langberg. I'm a member of the faculty here at the CS department, and I'm very happy to see that many of you guys could make it. And I thank you all for going through the traffic and making the effort to make it here to the Theory Day. We're going to have a full and exciting day ahead of us, a total of 8 talks from the morning until late afternoon, which I'm sure are going to be very enjoying and interesting. Before we start the formal talks, I'd like to remind everyone to shut off their cell phones. And I'm honored to invite Professor Gershon Ben Shachar, the president of the Open University, to say a few words.
Good morning and welcome to the Open University campus here in Ra'anana. I'm very pleased, very delighted to welcome you all to this Computer Science Theory Day, and we are very proud to host this conference at the Open University. In the past 3 years, we have devoted great many efforts to develop our computer science department, and I think we were very successful, and during this period we have recruited 5 new young scientists, researchers, I think excellent ones, and particularly we are strong in computer science theory, I believe. And I am sure that this development of our department, first of all, it makes our department one of the highlights of the Open University departments. And for the future, I envision a really strong and fruitful group of researchers. Because of those developments, I think it's very appropriate that we are hosting the Computer Science Theory Day at the Open University. I'm sure it will be very interesting. I looked at the list of lecturers, and we have some very distinguished speakers today. I'm sure it will be very enjoyable and very fruitful. And I will not mention all the speakers, but I'd like to welcome especially the visitors from overseas. Professor Tardosh, I don't know if she arrived yet. Soon. And Asaf Naor, is he here? Good morning. And I wish you very enjoyable, very fruitful discussions. Thank you.
Thank you, Gershon. I'm now very happy to invite Tamir Tassa, the head of the CS department here at the Open University.
Boker Tov, good morning, and welcome to the Israel CS Theory Day at the Open U. Israel has a strong community in theory of computer science, and Israeli researchers appear regularly in all the leading conferences in theory overseas. And we thought that it would be a good idea to have an annual meeting on theory here in Israel. Up until a few years ago, there used to be annual meetings, but to the best of our knowledge, they did not continue. So let's hope that this day will be successful, and maybe it will be a beginning of a renewed tradition. I would like to thank all the speakers that will give a talk here today, and as Gershon said, especially to those who came from afar, Asaf and Eva, who is still stuck in traffic, but hopefully every minute she will step in. Thank you, Gershon, the president, for supporting this day, and special thanks to Mike Landberg, who coordinated this day and gathered the distinguished group of speakers who will speak here today. I would like to say a few words about this place and about the department, because during my tenure here, I found out that it's not very clear how do we work. So the Open University is a distant learning institute, and we currently offer a bachelor, BSc, and a master, MSc in computer science. The method of teaching here is different, but the curriculum and requirements are similar to other universities. Each course is based on a textbook in English that is carefully selected from the textbooks that are used in similar courses in other universities in Israel and in major universities abroad. And every student receives that textbook in English with a teaching guide in Hebrew. And he or she studies by themselves, and they are supported also by guidance meetings and by a course website. Up until, as Gershon said, up until 5 years ago, we were very, very small, and only 5 senior faculty members and roughly 30 people in the academic teaching staff. But since then, we grew a little bit. Now we are 9 people in senior faculty, and in the coming year, we shall be joined by 2 additional faculty members. That's it. Let's start, and I wish all of us an enjoyable and interesting day. Thank you very much.
Good. Okay. So I'm very happy to invite our opening speaker, Yuval Rabani from the Technion. Yuval received his PhD in Tel Aviv in '93, joined the Technion, the computer science department in '95, and in between he was a postdoc at ICSI, at Berkeley, MIT, and in Toronto. Yuval's research touches many areas of the theory of computation and algorithms.
Hi.
And today he's going to speak about, we'll see it in a second, low distortion embeddings and edit distance.
So I'll talk about low distortion embeddings for edit distance, joint work with Rafi Ostrovsky from UCLA. This should work. Okay. Let me start by explaining what edit distance is. Suppose we have 2 character strings, x and y, over some alphabet, and for the entire talk you can think of the alphabet as being 2 symbols, 0 and 1. The edit distance between x and y is the minimum number of edit operations that are required to convert x into y, or vice versa. So of course this definition depends on the particular choice of edit operations, and one standard choice is to use 3 edit operations: insert, delete, and substitute. So insert means adding a character somewhere in the string, delete is removing a character somewhere in the string, and substitute is flipping the bit in a particular position in the string. There are other choices of edit operations that define variants of this distance, but we won't discuss them here today. Edit distance comes up in many different applications. I'm not going to go into these applications, but some of them all of you know, such as fixing spelling mistakes. So the choices are usually chosen from a list of, if you typed something that doesn't look like a word to whatever word processor you're using, it often offers you corrections, and the possible corrections are chosen from the dictionary according to some version of edit distance. Then the other big area where this comes into play is comparing edit distance. So if you want to know how far you are from a chimpanzee, you can compare your DNA to that of a chimpanzee, and a standard way to do it is to measure the edit distance between the 2 strings of DNA. There the alphabet has size 4. And there are other areas where edit distance appears. I want to go briefly and explain some of the history of edit distance. So it was first mentioned in a paper of Levenstein in 1965 as a way to compare 2 text files. Then somewhat later, the simple dynamic programming algorithm that most of us or all of us are familiar with was discovered. So this gives an order d square time algorithm to compute the edit distance between two d-bit strings. D here will always denote the number of bits in the string. And we will always assume that the two strings have the same length, even though everything I say can be generalized to strings of varying length. So this algorithm is essentially the best algorithm that we know for edit distance in the most general case. The only small improvement due to Mashek and Patterson, I don't remember all the names here, but see, they're easy to figure out, shaved off a log D factor in the case that the alphabet is bounded, for example, when it's just 0 and 1. But for arbitrary alphabet that could depend on the length of the string, the dynamic programming algorithm is the best we know. And this is probably one of the biggest complexity gaps in sort of a nicely defined problem that is relatively easy to solve. There's been some relatively more recent developments, so the question now is what can you do when the edit distance is small? And the best thing that's known is that one can compute the edit distance in linear time if it's below root D. So there's an algorithm, actually a simple algorithm, a modification of the dynamic programming algorithm that computes the edit distance in time D plus the edit distance squared. Now, by the way, in between these 1980 and 1998, there was also a lot of work that led to this. Much of it was on parallel implementations of edit distance computation. Then, I guess the new millennium, people started looking at the problem from a different perspective, and they asked about approximating edit distance. So computing edit distance exactly, we don't know how to get below this d-squared algorithm. That's pretty annoying. What about computing edit distance approximately? So the first such result of Batu et al. That actually triggered this renewed interest in edit distance this decade, showed a sublinear time algorithm that can distinguish between edit distance below d to the epsilon for arbitrarily small epsilon and omega of d. So it's not exactly d. What I mean here is linear edit distance versus something smaller than any polynomial, than any power. There were later results in this vein, so you can actually compute an approximation in nearly linear time, and the best such approximation that's known is about d to the 1/3. So this is more or less where the problem stands now. If we want to compute edit distance exactly, takes d squared or d squared over log n, and if you want to compute it approximately in linear or near linear time, you can only do so with a rather poor approximation. Now, there are other questions that one can ask about edit distance, and in fact, in this talk, these are questions that motivated this work. You can ask about the communication complexity of edit distance. So suppose Alice gets the string x, Bob gets the string y, and they want to compute the edit distance between x and y by communicating just a few bits. Can this be done exactly or approximately in terms of the result that they can show? A similar problem is that of sketching, which is equivalent to one-way communication complexity with shared randomness. So you want to compute a short sketch of the string such that if you compare the sketches of two strings, you can estimate their edit distance to some extent. Previously shown paper of Yosef et al. Gave a way to sketch string so that you can distinguish between edit distance below k and at least k times d to the 2/3, where k is an arbitrary integer. And then there's the question of nearest neighbor search. So you have a database of n strings. You're expecting to get query strings. You want to pre-process the database so that you can quickly answer queries. And there are some previous results in this vein that give a d to the epsilon approximate nearest neighbor search for arbitrarily small epsilon. So that's more or less the highlights of research on edit distance, older and more recent. Now, what I'm going to talk about today is embedding edit distance into some norm space. And the reason that we ask this question, of course, the real reason is because we need something to do and produce papers. But sort of as a side motivation, we know how to solve many of the problems that I mentioned earlier on when we have points in a normed space, in some high-dimensional normed space, for specific normed spaces. So if we can represent edit distance approximately in such a normed space, we've solved these problems without working hard, and that's, of course, always something we want to do. But, of course, we have to pay the factor that will go into the embedding itself. So the embedding might distort the distances, and we'll have to pay that factor in the approximation that we achieve for edit distance. So a natural candidate normed space to embed edit distance into is L1. And for the sake of this talk, just think of L1 as being the Hamming distance on the binary cube. So superficially, it looks a little bit like edit distance. It's just edit distance with one edit operation, substitute. So there are no inserts, no deletes, only substitutes. That's the reason why L1 is a natural candidate. And moreover, we know how to solve the previously mentioned problems in L1, so that seems like a good candidate. Now, we want to measure the quality of the approximation. And we'll measure the quality of the approximation, of the embedding, by its distortion. So what's the distortion? The distortion is a product of two factors. The first factor is the Lipschitz constant of the embedding. That measures the expansion of distances. So it's the ratio, it's the maximum ratio between a distance in the image and the original distance. And we multiply this by the contraction, which is the maximum ratio between the original distance and the distance in the mapping. So we want distances not to expand too much and not to contract too much. That's basically what this measures. We want the distances to be up to a scaling factor approximately preserved. This is what I'll show you here, if I have time. We'll show an embedding that gives the following distortion, 2 to the order square root of log d log d. And this function, aside from being the most natural candidate for the distortion, is interesting because it's smaller than d to the epsilon for any epsilon. So it beats anything that was previously done on approximating edit distance in these situations that I discussed earlier. This is smaller than any d to the epsilon.
So this improves all the approximation algorithm?
It improves the communication complexity, sketching, and nearest neighbor search for edit distance, yes.
Approximation of edit distance that was on the first slide?
No, because computing the embedding can't be done in sublinear time. So in fact, it doesn't improve that. Now, in order to compute the embedding, if given a single string, it takes a time polynomial in D to compute the embedding, and therefore, of course, we can measure approximately the distance between two strings by embedding them, but that might be somewhat worse than actually running the simple dynamic program. And this implies all of the results that I've just mentioned. I won't go over them. So we'll plunge straight into the embedding itself. I'll explain how the embedding is constructed, and then we'll analyze some of it or more of it if we have time. I hope someone will mention how much time I have left. Then finally I'll mention some later results and some new stuff that's been going on. So here's the embedding. The first step is very simple. We take our string and we partition it into blocks of identical length b. So if the length of the string is not divisible by b, some of the blocks will be of length b plus 1. So here is a string, and the colors code the blocks. And now we're going to deal with each block separately. So b will be defined later. And from now on, we're just looking at a single block and doing some things with that block and ignoring all the other blocks. So here is the first block. We're going to take what is called shingles. So shingles are just substrings of this string that are shifted by 1. And we take all the possible shifts. So we take S shifts. S is another parameter that we'll soon define. And the length of each shingle is exactly what would make these S shifts fit into the block. So it's exactly the block length B minus S plus 1. So we take all the possible such substrings in the block. And this gives us a set of strings that is listed at the bottom there. Of course, this could be a multiset because the same string could repeat itself several times if the string is periodic. So we look at this multiset of strings. This is the first step that we do. And now, each of the strings in this multiset is shorter than the original string. So the original string had length d. This string has length b minus s plus 1, where b is something much smaller than d. And s is going to be something much smaller than b. So we take each of these strings and recursively embed them into L1. So we assume that we have this construction is inductive, and we assume that we've already constructed the embedding for shorter strings. Of course, if the string length is constant, there's a very simple embedding. You take the identity map, and that preserves distances up to a factor, which is the length of the string, which is a constant. So at some point, it's easy to embed at a distance approximately. And from there, we build inductively an embedding for longer strings. So we take each of these shingles and embed them into, in fact, the Hamming cube. So it will be useful to think of the embedding into L1 as an embedding into the Hamming cube. And I'll denote the result by sigma 1, sigma 2, sigma 3, and sigma 4. In this case, S is taken to be 4. But in general, it might be larger. And the reason I don't explicitly show the strings is because they're going to be much longer and more complicated. So now we have a set, or actually a multi-set, of points in the Hamming cube. So just longer strings. And we take this multi-set and we map it to a point in L1. So we use some mapping psi that maps sets of strings into L1, sets of points in some dimension n cube into L1.
So you don't care about the ordering of this?
No, we don't care about the ordering. We just treat it as a set. It's a set of strings, and the mapping psi maps multi-sets of strings into L1. And of course, I have to specify what the mapping psi is, so this is the next thing we'll do. But okay, before I do that, let me just define now the parameters, and then we'll deal with this mapping psi. The block size that we're going to take, B, is d over 2 to the square root of log d log log d. The value for S, in fact, we're going to use several values for S. So S is going to be a power of log d, and we're going to take all the powers of log d between log d to the 0, which is just gives us 1, and a power that is at most b over log d. So we're going to take all the powers of log d that have values between 1 and b over log d as S. You can think of S as being a scale. So each value of S will try to capture a different value of edit distance in that block. And now each block, so we have 2 to the square root of log d blocks. And each value of S, among these powers, there are about log d over log d of them. Each of these values generates a set of coordinates by taking these shingles, mapping them to the Hamming cube, and using this map psi, which of course depends on S, because the mapping psi would be different for different length strings. So now let's talk a little bit about psi. I'll first define the properties that we want from psi, and then explain how to construct psi. So consider two sets, S and T, that have size S. So these are two sets of strings on which psi can map to the Hamming cube. We're going to define a distance on multi-sets of strings in the following way. So you can ignore the formula. I'll just explain what it means. Here is the set S, and here is the set T. So both contain, in this case, 4 strings. S equals 4. We look at a matching here. So this is a particular matching between the two sets. And we're going to look at all possible matchings. And in a matching, we're going to define the length of the edge to be proportional to the Hamming distance between these two strings. Well, not exactly, because we take the Hamming distance and multiply it by some constant. But then we cut the Hamming distance at S. So any distance which is if this turns out to be more than S, we're going to just take S to be the distance. So the distance of an edge is never greater than S. But if it's below S, then it's going to be proportional to the Hamming distance between the two strings. And now we take the best such matching. So we take a min-cost matching, and the distance is just the average weight of an edge in that matching. So that's going to be this distance between sets of strings. Now what we want from our embedding, from our map psi, is written below. We want two things. We want two properties. The first property is that if we take the images of two sets and we look at the L1 distance between them, we want this to be at most the original distance, at most this distance, times a constant. So this means that we don't want distances between sets to be stretched too much by this embedding. They could shrink a lot, on the other hand. That's okay. But on the other hand, if all the edges in the matching or in any matching are long, are at least S, so that means that all the Hamming distances here are large. Between any string here and any string here, all these Hamming distances are large. In that case, we don't want the distance to shrink too much. So in that case, we want the map to have L1 distance bounded by S over 2. And the constants here could be changed. They're not important. So this is not a distance preserving a map, because if the distance is relatively small, it could shrink a lot. But it does maintain that if the distances are huge, are very large between all these pairs, they don't shrink. So how do we do this? Here is an inefficient construction. So this is a non-constructive way to do this. We'll need to, in order to actually get an algorithm for the embedding, we'll need to do something slightly different. But for the sake of the talk, this is good enough. So think of a set I of a number of positions in these strings. So we just take numbers between 1 and the length of the string. And I is just a sequence of such numbers. N is the length of each string in the set. And this is the number of positions that we take, which is not very important. And Z is a particular assignment of values of bits to these positions. So Z is a string that has this many bits. And now for every possible value of I, so I is just a sequence of positions, and Z is a value of bits for these positions, every such pair will generate a coordinate in our map, in the map psi. And the value of this coordinate will be the number of strings in the set that have exactly Z in positions I. So if we look at the positions denoted by I, we see exactly the string S. And of course, for most of these coordinates, the number will just be 0. There will be only a small number of coordinates where the number is not 0. And then we have to scale this, which I won't go into. So this is the map. All the strings in the set S. Yes, we just look at the strings in the set S, and we look if there's any string that in position I contains, in positions I contains the string C, we count it, and we count how many such strings there are. So this is the map. The analysis I'm not going to go into, but it's just a simple probabilistic analysis. We just look at our two sets, and we measure the probability that we get the same substring Z for a random set of positions I. And of course, since we're going over all the I's, we're going to get exactly this probability as our difference. I'll skip that. So now let's now we've completely defined our embedding, right? So we partition the string into blocks. In each block, we take shingles for various values of scale S. We look at the multi-set of shingles. We recursively embed that into L1, and then we use the map psi to embed the set that we get of strings S back into L1.
This only shows these two properties that you wanted.
Yes, exactly. So this shows that the mapping psi has the two properties that we mentioned. Now we want to show that this embedding, in fact, approximately preserves edit distance. So there are two crucial observations here. The first observation will show the upper bound, the bound on the expansion, and the second observation shows the bound on the contraction. And I'll explain that in some more detail soon. So what is the first observation? Let's look at a particular block. So I'm looking at the same block in two strings X and Y that I want to compare their edit distance against their L1 distance in the embedding. So this is this block in these two strings. And let's look at the edit distance computation for these two strings. So that finds that there are some edit operations that occurred in this particular block. Let's say that K edit operations occurred in this particular block. So what does it mean? Well, there could have been some edit operations that happened before the block. And that could have changed the alignment of this block in the two strings. So in this particular case, for example, perhaps two bits were deleted from the second string before we ever reached this block. And therefore, these two bits, the first two bits of the block, actually match bits in a previous block. And then we have a portion that matches in this block, and then, there are these two extra bits here that match the next block in the first string. But in this segment, we know that there are k edit operations, and in fact here we see there was exactly one edit operation, a substitution. So now all the shingles that fall in this segment, inside the segment, they must match with edit distance at most k. Now, how many shingles don't fall in this segment? The number of shingles that don't fall in this matching segment is at most the number of edit operations that occurred before this block. And therefore, it's at most the global edit distance between x and y. So at most edit distance xy shingles in this block would have, if we take the shingle and the matching shingle, what I mean by the matching shingle is the shingle that is shifted by the right amount, two positions in this particular case. If we take these shingles, at most edit distance xy of them will match with edit distance greater than k, and the rest must have edit distance at most k. So that's the first observation that we have. That we have that if the edit distance in a block is small, then we have a good matching, a matching where most of the edges in the matching have small distance. The second observation is also simple. If any two shingles from these two strings, if we take a shingle from here and a shingle from here, and they match with a small distance, so we take shingles alpha and beta, and they match with edit distance between them, and that's small, then we can convert one block to the other paying a small amount, because what do we have to pay? For matching this shingle, we have to shingle alpha to shingle beta. We have to pay the edit distance between them, and then we may need to remove s bits from in the beginning or the end from this string, and s bits in the beginning or the end from this string. So that's another 2s operations, and therefore the two blocks match with 2s plus edit distance alpha beta operations. So these are the two crucial observations that explain why the embedding works. Let's now see exactly how the first observation leads to the upper bound and the second observation leads to the lower bound. So suppose we've chosen a scale s that is at least the number of edit operations in the block. Lower scales will contribute negligible cost, so I'm not going to go into that in detail here. So we know from the first observation that we have a good matching. We have a matching where most of the edges have cost k, and there's a small number of edges that have high cost. Now, the bad shingles, these are the shingles that are matched through the bad edges. What is their total contribution to the distance between the sets S and Y? S and T. Well, there are at most edit distance XY such shingles. We've truncated the distance so that it's at most S, so each one of them costs us at most S. And then since we're averaging over all the edges in the matching, we have to divide by s. So the total cost of the batch shingles is the edit distance between x and y. And this is what we're paying in each block, by the way. Then what about the good shingles? Well, there are at most s of them, of course, because they're s shingles altogether. Each one of them had edit distance k. And therefore, when we used the embedding recursively, we expanded this edit distance by a factor which is at most the Lipschitz constant of the embedding for strings of length at most b. So we're paying this constant times k, and then times there was a constant there in front of the Hamming distance, so that's the constant, this constant. So this is simply the length of a good edge. And this is the cost of the good edges. Now, when we sum this over all the blocks and all the values of s, we get that the expansion in the embedding is this thing contributes the number of blocks times the number of values of s times the edit distance. So the contribution to the Lipschitz constant is just the number of blocks times the number of s. So here you see that we don't want to have a lot of blocks. This part, when we sum this over all the blocks, we're summing these values of k over all the different blocks, and they sum up to, at most, the edit distance between x and y. And I'm bluffing here a little bit. You have to pay a constant of 2 here. But in general, this is the number of edit operations in each block. So when you sum it over all the blocks, you're summing over all the edit operations, and that's the edit distance between x and y. So when we sum this over all the blocks, we just get the number of different values for s, times this logarithmic factor, which is at most log d, times the Lipschitz constant for much shorter strings. So we get a recurrence relation here, right? That relates the Lipschitz constant for the embedding for d-bit strings to the Lipschitz constant for the embedding for strings of b-bits, where b is much smaller than d. Now, I don't have much time, so there's a similar analysis that I won't go into that bounds the contraction of the embedding and gives a recurrence relation for the contraction that is written here below. And now we have these two recurrence relations. So this bounds the expansion, and this bounds the contraction. And you can see from these recurrence relations that we need to balance two things. We want to balance we don't want the number of blocks to be large because it affects the Lipschitz constant here. And on the other hand, we don't want the recurrence to be very deep because then we'll pay a lot for these factors here and here. So the best balance that you can achieve for this recurrence is to take the number of blocks to be 2 to the square root of log d, log d, and both of these recurrences solve to this function. So their product is also a similar function. And this gives us a bound, the bound that we claimed on the distortion of the embedding. And the recurrence depth is going to be square root of log d over log d in this case. We're near the end of the talk. I just want to mention some additional points and some additional results. So first of all, the construction of psi, as I've shown it, is highly inefficient. We're generating an exponential number of coordinates because we're taking all possible tuples of bit positions. That's already exponential. And for each of those, we're taking all possible assignments of values, another exponential. So that's, of course, an inefficient embedding because it takes a long time to compute the map of a single point. But you can actually sample the coordinates of psi cleverly and construct the embedding effectively. Now, if we want to generate an embedding that fails with probability delta for a single pair of strings, x and y, then we'll need dimension about d log d, if delta is a constant. So if you want to embed the entire cube, you need delta to be 2 to the d choose 2. So if you plug that in here, you get an embedding into something like d square dimensions. Now, what about lower bounds? The best lower bound that's currently known for embedding into L1 is omega of log d. So there's a huge gap here between the upper bound and the lower bound, and that's a major open problem, of course. If you want to, if you insist on embedding into Hilbert space because you like Hilbert space, then that's known that the embedding is very poor. And the reason is because you can encode a cube of somewhat, a Hamming cube of somewhat smaller dimension into edit distance. Now, we also mentioned communication complexity as part of, as one of the applications that our embedding solves. There's been some further work on that. So this is Andoni and Krautgammer. They showed that, in particular, I think they have more general claim here, but in particular, they showed that if Alice and Bob, Alice holds X, Bob holds Y, they exchange just a constant number of bits, then you can't estimate at a distance better than log d over log d. And on the other hand, if you're willing to send, if the edit distance is small, you can actually have very good communication complexity. So you can send, if the edit distance is a constant, you can send the polylogarithmic number of bits and compute the edit distance exactly, not approximately. And I guess this concludes my talk.
Okay, our next speaker is Muli Safra from Tel Aviv. Muli did his PhD at Weizmann in '89, and then joined Tel Aviv University after passing through, I think I might MIT, Stanford, and IBM. Muli's research focuses on complexity theory, in particular on the classification of approximation problems, and the theory of PCPs, probabilistically checkable proofs. And today Muli will speak about...
So I'll talk about all of these four different notions and the connection between them. I'm sorry, not only that this is a bit too early for me, but it's also the case that I'm a bit sick, so you might get better schedule because I'll be short. Okay. So here's the world according to complexity. We have the class P and the class NP and co-NP. Then we have the class of all the NP-complete problems. This is well established, and we've managed to show many problems either in P or NP-complete. But the question is, what do we do with problems that are not in P and are not NP-complete? So, for example, one well-known problem is factoring. You need to find the prime factorization of a number of n bits. But another is some lattice-related problem. One of them is the shortest vector problem in the lattice. So this problem if you want to approximate it within some factor that is known to be in P intercept co-NP, but for others it could be, it's not known to be in P, but it's also not known to be NP-complete. And here is immediately a question. So these two problems, factoring, for example, is quite unlikely to be NP-complete, just because of the fact that it's in NP intersects co-NP. Just the fact that factoring is an NP intersects co-NP implies that we don't know whether it's unlikely to be NP complete. Because if it were NP complete, then NP would be equal to a co-NP. It's also the case for SVP for some factors. And the immediate questions I want to pose is whether these two problems are related. So we have two problems that are not known to be in P. They're quite unlikely to be in P. They're not known to be NP complete. And at least one of them is unlikely to be NP complete. In fact, for some factors, also the SVP problem. And the question we like to pose is whether maybe they are at least connected. Maybe they are in P, maybe they are in between P and NP complete. And there are two very good other examples for problems that are at the same state. One of them is a unique A problem. I'll define it in a minute. And we've managed to show recently quite a few problems to B whose complexity is related to unique game. And the max-cut problem, which is well known, but I also define it in some bit of a slight different way. And the immediate questions I like to tackle whether these problems are related. Can we show some reduction from one to the other, or at least show that they're, ultimately show that the complexity is the same. So here is a general framework by which to define some constraints problem. These are very specific. This is a very general definition, but it's limited. It doesn't include all of the constrained problem that we can have. So here's a problem. We have a graph, so vertices and edges, and we have a set sigma of values that we can assign to the vertices of the graph. Let's call them colors. And we have a set of constraints. For each of the edges, we have some constraints that limit the two colors that could be at the end of the edges. Not all pairs of colors are accepted. So that's how we define phi as a set of constraints. And there's two, when we look at solutions, solution would be coloring of the vertices. There are two versions to this general framework of problems. One of them is that we ask to color as many as possible of the vertices. Some of them get color, some of them do not get color. So that's coloring. We color the vertices by sigma or leave it undefined. However, we require then that all constraints between colored vertices, all edges in which both ends are colors, the constraint must be satisfied. And what we try to do is optimize or maximize the parameter, which is the fraction of vertices that are satisfied, that are colored. So we'd like to color as many as possible of the vertices so that all constraints are met. That's one option. And if you see, you can easily see, I won't show each of them, but many of the constraint problems we know can be described in this way, like the clique problem, three-sub problem, vertex cover. Another variant of this framework is where we in fact color all vertices and try to satisfy as many as possible of the constraints. So we've colored all of the vertices, and what we count as the optimization parameter is what fraction of the constraints are met. And you can see that one example we'll show in a minute is max-cut can be described in this way. Okay, so is it clear what I say when I say constraints graph? This is constraint graph, and that's a general framework. And then we have to define some gap problems. So here is the gap unique game problem. It's the parameter epsilon and 1 minus epsilon. We'll see in a minute what it means. So we are going to look at solutions. Solutions are coloring of the vertices. And we see what fraction of the constraints are satisfied, and we divide it into two extreme cases. One is when almost all of the constraints are satisfied. So more than 1 minus epsilon of the constraints are satisfied. That's a good case. This is what we have here, the 1 minus epsilon. And the other case, the bad case, is when you have an epsilon fraction. Any assignment, any coloring could satisfy at most epsilon fraction of the constraints. There's some gap in between these two values, between epsilon and 1 minus epsilon. And in this case, we don't care what the outcome of the algorithms that solve this problem. The reason we look at these problems is because by showing that such problems are hard, we immediately get that approximating this problem is also hard. Since if you take suppose you want to take the unigame problem and you want to approximate it, what you'll do, suppose you have an approximation algorithm for it. If the fraction that it can be satisfied is 1 minus epsilon, and you get take an algorithm that does not satisfy all of them, but satisfy 1 minus h times epsilon, then when h is some constant, you'll know that you cannot actually confuse between the two cases. So if you started with 1 minus epsilon satisfied, you get solutions that satisfy at least epsilon fraction of them. And then what you can do is just give the correct answer. So that's a very interesting problem. The question is whether this problem is, okay, actually there's something missing here in the definition of unigame, which I didn't actually write down here, which is that the constraints are of some specific structure. If you look at each edge, the constraint that is imposed is that for every color on the left, we have exactly one color on the right that could satisfy the constraints, and also vice versa. So it's a permutation of the colors. This problem is not known to be in P. And actually, some people think that they can actually show that it is in P, but I doubt it very much, that you can actually show such a problem to be in P. It will be very surprising. This problem is also not known to be NP hard, and actually I would be surprised if it is shown to be NP hard. It's quite unlikely that with this specific structure, when you have permutations of constraints, so this means that the color of one vertex determines exactly what color you need on the other side, that you can actually get the NP hardness by this. This will be very difficult. We got almost to that situation, but it took a lot of work, and I would doubt that this could be shown. So it's quite reasonable to think that this problem is, in fact, not in P and not NP hard. It's in between. And now the question is, what do we do with it? And the interesting part is that this problem was shown to be some other problems. So the complexity of this problem is really completely open. There's nothing we know about it. It's between P and NP complete, and there's nothing we can tell. What people could do is show unigame hardness, reduce this problem to another problem, and do that for some problems that are not known to be NP hard. And this is very productive, because these problems were not shown to be hard. Once you show their hardness with respect to unigame, you know that at least they are the same complexity as that. Here is another problem that we can consider, and this is a max cut. We can describe it in the same way as just a special case of the unigame problem. We take the vertices and we assign them two colors, black and white. And the constraints require that the two colors at the end must be different. So if you actually color the vertices of the graph with two colors, you actually impose some cut on the graph. And if you measure what colors are different, this means what edges are in the cut. And I put this parameter specifically as a 1 minus square root of epsilon. 1 minus epsilon is actually very interesting. It's not, I'm not sure I have time to explain why those are the right parameters, but for small enough epsilon, these are the right parameters. So this means that you must accept all graphs in which the cut is larger than 1 minus epsilon. You have a cut in which almost all of the edges are in the cut. So it's almost a bipartite graph. There's only an epsilon fraction of the edges that are not in the are within those two parts that you divide the graph into. So it's almost bipartite. And there's an extreme case in which the graph is very far from being bipartite. If you actually, whichever way you divide it into two sets, you'll have only an epsilon fraction of the, sorry, 1 minus square root of epsilon fraction of the edges in the cut. Let me say it again, it's not so far from being, right, just by random assignment you'll get 1/2. But what I'm saying is, let me just say it again because I said it too extreme. You have one case in which you know that the graph is epsilon close to being a bipartite graph, and the other case in which you know that in every cut you'll have at least square root of epsilon of the edges outside of the cut. And again, we have the gap. We don't care in between. And what we know as NP hardness goes for this problem is I just put 1.01, but I'm not even sure about that. It may be even a smaller constant, but let's assume that. We know that given a graph, which is epsilon close to being a bipartite graph, you can actually have, it's actually amazing to think that you have a graph in which it seems like you'll be looking at it and you'll see immediately how you divide it into two parts. The only thing we know that it's NP-hard is if you find the cut, is to find a cut in which the only 1.01 times epsilon of the edges are outside the cut. So there's a huge difference between this problem over here, when we look at 1.01 epsilon, and the square root of epsilon over there. And epsilon becoming very small, this is a huge difference. And in between these two values, it's quite completely wild. We don't know anything, actually, about this problem. And the question is whether these two problems are related. Can we show, so these two problems for 1 minus epsilon, 1 square root of epsilon for max cut, and unique gain from 1 minus epsilon and epsilon gap. These two problems are in the same state. They are not known to be in P. They're not known to be NP-hard. And the question is, maybe they're just there. Maybe it's not the case that you can actually take any problems you'd like and put it either in P or NP-hard. And then we'd like to actually show that these are related. Maybe the complexity is the same. This would mean that we have some classes in between P and NP complete that are independently.
What about epsilon to the 3/4?
It's the same.
Same as this.
You know NP hardness for some small constant times epsilon. We know unique game hardness, which I'll say in a minute, for square root of epsilon. That's a famous result I'll mention in a minute. And in between, it's widely unknown. We don't know better than a unique game hardness. And we certainly, I actually would doubt it very much that you can actually show NP hardness for anything larger than some small constant times epsilon. It's the same state, and I'm trying to say, maybe that's a message that if you remember, will be, actually, I'll do my job and then collapse. The point is that these problems are, I think we have to really seriously consider the option that they are neither. We tried very, very hard to actually get something better than some small constant times epsilon NP hardness for this problem. And I would doubt that you can actually do it in today's technique. So we have a huge, not gap, I shouldn't use the same word, but a huge scale of parameters in which the problem is not known to be either in P or NP hard. And what I'm saying is that at least what we can do at least is to show that these problems are related. This would mean it will be some, if you think about it, it's the same way as showing that the problem is NP hard. We don't know what's its complexity. We just say, okay, these two problems are related in complexity. If we can show that for these problems, it will be great. And I wish we could have. Okay, so actually, I think I'm not sure I'm mentioning it, so let me just say here that in fact there's a paper by Guy Kindler, Subhash Kot, Elchan Mossel, and Ryan O'Donnell that in fact shows a reduction from unique gain to max cut with these parameters for small epsilon. So we know that this problem is unique game hard. The question I'd like to pose is whether we also be able to show the reduction in the other direction. Namely to show that in fact, if we show a reduction in the other direction, this would mean that in fact, unique game really is the max cut problem, which is really classical. Many people have looked at it, and they couldn't show better algorithm or better hardness result. Another point about the epsilon squared of epsilon, which I should have mentioned earlier to Natis, is that this is what you get from the Gomez-Williamson algorithm. That's the best approximation we can get. For small epsilon, this is a factor that the algorithm gives. So here is a technique. It's a very interesting technique that we may want to use in order to show a reduction from max cut to unique game. It's called a parallel repetition. And I can define it in these terms. U to the L has vertices. Each vertex of that problem is a sequence of L vertices of U. Each edge is really L edges of U. You just take edges. If you take L edges, you have, suppose they are direct, you think of them as directed edges. You have the left side and the right side. On the left side, if you take all of the L vertices, you get a vertex of V to the L. On the right side, you get L vertices that are also in V to the L. So you get an edge between those L sequences. The coloring of these vertices is just L colors, one for each vertex. So we think of them as coloring of the original constraint graph problem, one color for each vertex. And the constraints are the natural constraints. If you look at L pairs of colors and edges that correspond to them, each of the edges imposes some constraint on the color that could be at its ends. And you just take the end of all of these constraints, make sure that all of these constraints are satisfied. And here is a very good question. What we like to say is, suppose we have some constraint graph U that is 1 minus epsilon satisfied. There is some assignment, some coloring that satisfies 1 minus epsilon of the constraints. What fraction of U to the L could be satisfied? So here's a trivial lower bound. What you can do is take the same assignment that satisfy 1 minus epsilon and just give all L vertices the same color according to that coloring. And what you'll get is 1 minus epsilon to the L. That's a very simple lower bound. It's a straightforward assignment. And what Ran Raz and later Hollerstein Ran Raz actually proved this theorem, but Hollerstein actually gets a little bit better parameters. So what they could prove is this funny-looking upper bound, which is 1 minus epsilon cubed to the power of L over log of the size of the alphabet. So I won't mention the log of the size of the alphabet from now on, although it's very important. It's actually otherwise, it's really inherent in this problem. But what really bothers us, in order to apply such a reduction from max cut to unique gain, is this cube at the epsilon. If we could get it linear, 1 minus epsilon to the power of L, we'll get a matching lower bound and upper bound. So that's what we like to do, and what we'll get by that is an improved upper bound. Now, there is a paper by Feige, Guy Kindler, and Ryan O'Donnell. Two of them are here. And what they show is that if the question whether this can be improved relates to some other geometrical problem, which is called the form, which I don't have time to go into. So it's an interesting question whether this can be improved. And what we'll say here is look at some variant of the parallel repetition. This is another point that I'll mention to those who've been working on this problem for 10 or 15 years. It's a very difficult problem and interesting. There could be many variants of the parallel repetition technique. What I just showed is the simple variant. You just take L edges and you apply them. This is the construction you get over there. But here I'll show you just a slight variation, and you'll see that this makes actually our life much easier. And the question in general is whether there are some other variants of this technique. So lazy parallel repetition is apply the same construction, although before you do that, you take the graph and you add self-edges to the graph. And suppose you have weights on the edges, so the weight of the edges of the self-loops would be some constant, say half. And then just apply the parallel repetition the way you find it over there, just regularly. This changes somehow the construction. It's not the same, and some of the lower and upper bound are not, actually the lower bound is really immediately the same, but the upper bound could be actually improved. And here is a theorem that I like to, maybe if I have time at the end and I survive I'll show you that theorem. The proof is kind of, it's not very complicated. Looking at an upper bound, it's a very surprising upper bound. The upper bound is 1 minus epsilon. We'd like to have 1 minus epsilon to the L. What we get is 1 minus epsilon to the gamma L, where gamma is the expansion of the graph. It's the spectral gap of the graph, if you like. And this is first, I like to say it's very surprising that where does the expansion of the graph comes into this funny looking constructions and proof. But once you look at it, you'll see that it actually makes sense. This is, in fact, what we'll get. And not only that, I'll mention in a minute, maybe in the next slide, that there's some other later papers that show why this is, in fact, essential. Okay, so this means now that if you have a graph, if your maxed graph is a good expander, you can get a very good reduction from maxed to unique gain. You just apply the parallel repetition. What you get if you apply the parallel repetition is a unique gain instance, because you look at all the colors at the left, you know immediately what you want from the color on the right. It will be an excellent reduction from maxed to unique gain, and in fact will give us the parameters we want. This is as long as gamma is constant. When gamma is small, when the graph is not a very good expander, this will become worse and worse, and eventually it's not really very meaningful. Now, one could hope that we can show that it is NP-hard to approximate max cut, even for graphs that are expanders, but I'm not at all sure that that's the case. So this could actually show that unique gain is hard in some other way, but it's a bit doubtful. Okay, so here's what I claim here, and I'd like to say that it's quite interesting and surprising, that in fact you can apply the parallel repetition, start with a max cut problem. This actually theorem does not only apply to the max cut problem, it applies to any problem. It doesn't even apply to the unique gain instances, it applies to any constrained graph. And you can apply the construction, and only what you have to pay is gamma, the expansion of the graph. a spectral graph of the graph. There are too many gaps. Okay, here's another interesting variant of the parallel partition, which was suggested by Uri Feige and Joe Killian. And this is what's called a mismatch. Suppose what you do is you choose L vertices on the left, and you choose L vertices on the right, but you don't require, in order to have a constraint between them, you don't have to require that you have L edges between them, as I did before. Suppose you just require that there's half of the edges between them. So half of the vertices on the left are free of constraints, and half of the vertices on the right are free of constraints, and only half of them are constrained. That could be it's a very legitimate construction of the parallel partition, and it could be very useful to show some good upper bound for that construction. Okay, is it clear what I'm saying? So, okay. I should have asked before.
What are the valid choices of color?
It's the same as the parallel partition I described before. Okay, so let me just repeat that. What we did in parallel partition is we said, suppose we have a graph, a constraint graph, coloring. Now what we'll do is we'll think of our new vertices as L sequences of vertices. So L tuples of vertices. L vertices. Now we can actually apply some constraint on them. How do we actually get a constraint in the regular parallel partition? We say, okay, here when we'll put a constraint between two L vertices, if there's an edge between the first vertex and the first vertex here, the first vertex, the second on the left and the second on the right, and so on. What would be the constraint then? The constraint is a natural constraint. You just take every one of these L edges, and for each of them you just apply the constraint that is clear from the constraint graph constraints. You just apply all of them. Now I'm saying, suppose you take L vertices on the left and L vertices on the right, but you actually require there will be an edge between every one of them. You just require, suppose, it would even work if you just require there will be edges between half of them here and half of them there. And the constraint will be the same. So half of the L vertices half L of the vertices on the right and half L of the vertices on the left, you don't have any constraint between them. You just have half of the constraints, half L of the constraint between, these are the only constraints that you have. Is it now clear? Okay, this is a very legitimate parallel partition. It would work many times. One problem, which I should note, this will not maintain the uniqueness property. When we apply the regular parallel partition, if we have a unique gain graph, we get a unique gain graph. This is not maintained here. But never mind, this is a very legitimate. And I'm saying that a corollary of the theorem that I just mentioned is that we can actually get 1 minus epsilon. I'm actually neglecting some constant there. We can actually get for this construction, we could get 1 minus epsilon to the L, an upper bound which almost matches the lower bound. And how would we do that? So it is in fact rather simple. What we do is we add to the graph some good expander. We have some new edges. We apply some trivial constraints on those edges. We just accept whatever is in both sides of whatever colors. And we let the weight of these edges to be half of the edges of this expander. And now apply the theorem from the previous slide, the one that I'm hopefully going to show you a little bit. And you see that half of the edges are just empty constraints. They are not constraints that are completely trivial, and half of them are real constraints. In fact, in order to prove that, I actually prove you something stronger than what I did. In fact, what you need to do in order to prove that theorem is just apply the complete graph with weight half. What we get here is even better than that. The complete graph is a good expander, and you can get this. Now, one of the hopes that we had at the beginning is that actually you can actually improve these techniques in order to get rid of the gamma, the spectral gap of the graph in the process. This turned out to be not true, at least for the regular parallel repetition techniques. This was proved by Ran. He has a very nice example of how to construct such an apple bomb. So here's a question that I like to pose. One of the things we need to, since we know that this is what we'll be able to prove, one of the things we like to do is to apply different variants of the parallel repetition theorem and get maybe possibly some improved result. Another option is to apply completely different techniques, and this could actually come out of the analysis that I'll show you. And it's also possible that this is inherent in the technique. Okay, so let me actually just show you a schematic proof of the theorem that I just mentioned, which is that if you apply the parallel repetition theorem to a constraint graph, what you'll get is an upper bound on the coloring, which is 1 minus epsilon to gamma L. If you start off with a graph in which you can satisfy 1 minus epsilon of the constraint. And the proof is, if you just want to skim it, just go through show without details is rather simple. What we do is for every vertex V of the original graph, we look at all of the extensions of V, all of the sequences that contain V. Each of them gets some coloring, and therefore we get some color for V for each of them, for the vertex V for each of them. We divide those L sequences into two, vertices. We divide those vertices of the original graph into two sets. Those in which, if you look at all the extension, you get pretty much the same value. Say 99% of the extension give it the same color. You see, what we do is we assume 1 minus epsilon to the gamma L coloring, one that satisfies these many constraints. So we look at all of those in which the coloring is consistent almost everywhere. And we prove a relatively simple lemma that shows that the vertices for which the coloring does not have an overwhelming majority, say 99%, this fraction of vertices is rather small. How do we prove that? We just look at all of these extensions. If we look at all of these extensions, what we get is a graph. The graph has some expansion. And we know that just by the parameter gamma, this will be the fraction of constraint that will be dissatisfied. I'm not showing you the details, but this is not so complicated. What happened then is that we've just shown that almost all of the vertices get a consistent coloring, and then we have to show that two vertices that have a constraint between them, if they have an overwhelming majority, must have two values that satisfy the constraint between them. And that's also relatively simple. Okay, so I just showed you whatever I'm going to show you of the proof. I hope I convinced you it's relatively, it's not so complicated. And let's see, I'm actually ready for discussing what are the possible outcome of this. Okay, so the first interesting sort of philosophical question I should ask is, why does expansion get into this theorem? Why is it important why can't we prove it for general case, and why can we prove it for graphs that are good expanders? I'm not so sure why this is the case, but it seems to be a recurring theme. It seems to be true. The other, which then one can suggest, as you've seen in the corollaries that I showed you, that we can actually consider some variants of the parallel repetition, and for these variants we can get much better results, much better upper bounds. And the last question is whether indeed what I was trying to convince you that we should prove is indeed true. It is possible that there's some way to show that in fact max cut and unique game problems are not related. There's some inherent difference between them. And this would mean, if we still believe that they are both between P and NP complete, this would mean that there's some hierarchy over there or some relationship between them over there that we need to investigate further. Okay, I'm done.
I'm honored to invite our next speaker, Eva Tardos from Cornell. Eva received her PhD in Budapest in '84, and then after passing through MIT, she joined Cornell in '89, where she currently chairs the computer science department. Eva's research focuses on algorithms and algorithmic, more specifically on the design and analysis of algorithms and efficient methods for combinatorial optimization problems and graphs on networks. And today Eva is going to talk on bargaining and trading in networks.
Okay, so I'm going to talk about actually more of bargaining than trading on network, and let me tell you in a minute what they are. So generally, I like working on game theory these days, and I want to motivate or work on all kinds of computer science or computers motivated problems via understanding as a game theory that is thinking of the selfish behavior of different parties and the outcomes of games and selfish behavior. There are a lot of games like this that have been studied, and I guess for a lot of different contexts in networks. The ones that I'm mentioning here are more sort of internet related, that is browsers, routers, servers, how servers get configured, how the network gets configured. The one I'm going to be motivated by today is actually other ones in this list of different networks that we're thinking about. I'm going to mostly thinking about social networks or maybe trading networks. And I guess here are two examples of the kind of networks I'm going to think about for today. The example on the left is a social network, or a very simple incarnation of what implicitly is a social network, that is the email exchange network at HP Labs from 2005. And this one is an ancient social network of some sort. It's a trading network of trading routes around the turn of the century, at the turn of the previous century, I mean to say. Trading networks in Europe, that is the routes in which people followed trading. There is also, so this is sort of what's the topic going to be, is the social networks and trading networks. There is also sort of a game theory interest. So a lot of the work in computer science, that there's a big interest in modeling selfishness and thinking about selfish users. And most of this work, including most of my own work, is thinking of Nash equilibrium as the solution concept. Nash equilibrium is a strategy where everyone is sort of happy, and what I mean here is that for every player, if everyone else currently stays with their strategy, then they also prefer to stay with their own strategy, that it's the selfish best response or best solution given what everyone else is doing. What's nice about Nash equilibrium is that it exists, this is the original theorem of Nash's, but there are some other issues, or many other issues, that are not modeled by Nash equilibria, and I guess I'm going to, at least in a specific context, trying to address two of these issues a little bit. One of the issues is collusion. That is, remember up there it said that current strategy is best response for all players, and I guess what I really mean to say is for every single player when acting alone. It does not mean to say that when small groups or some groups of players collaborate with each other, they couldn't actually improve their life. In fact, often they can. And second is that even though it's very nice that equilibria always exist, sometimes there are many equilibria, and then there is what's called an equilibrium selection problem. So you sort of wonder which one is the predictive equilibrium, which one is the one that's likely to happen. So what people really would like to do, and what I'm going to talk about in a bargaining setting, is going to be mostly based on a joint paper with John Kleinberg that will appear in Stock. And it's modeling a bargaining behavior network. It's an example of a small group cooperation. So in that sense, it's addressing the collusion problem in a natural way. And it's going to be not, it's an example of a Nash equilibrium strategy, but a more specialized strategy than Nash equilibrium. I'm trying to address which of those equilibria are the likely behaviors and which are not. So in a way, I'm also motivated by the equilibrium selection problem. I want my model to be predictive, that is, to choose the behavior that people or these parties likely to engage in. So let's actually step back again. If we think about cooperation, what other cooperative game theory issues definitions one should know about. So remember, Nash was a strategy where a single player can deviate whenever it improves his or her own solution, and Nash equilibrium is that no single player alone can improve his or her own outcome. The simplest definition from cooperative game theory is that of a strong Nash equilibrium. A strong Nash equilibrium allows collaboration and says that a solution is a strong Nash equilibrium if no subset of players can coordinate the deviations so that every single one of them is happier after they changed than they were before. So this is a definition of, a stronger definition of Nash equilibrium. As you maybe already know, it feels what was nice about Nash equilibrium exists. What's not so nice about strong Nash equilibrium that it may not exist. It doesn't always exist, but sometimes it does. When it exists, it's nice. When it exists, it of course it selects one of the equilibria. If something is not a Nash equilibrium, it can't possibly be a strong Nash equilibrium either. So it selects an equilibrium and often selects one that's better in different kind of ways. It still might have an equilibrium selection problem. This still may not be unique, or may easily not be unique. And actually often has a fourth problem that I didn't somehow put on this slide, a coordination problem, depending on how hard it is for these subsets to find each other. If very big subsets have to coordinate in order to make the steps, that might actually be hard for a user. So a lot of cooperative game theory got around the first problem, that the strong Nash equilibrium may not exist, by getting away from this definition. And instead of defining things in terms of Nash equilibria, they try to define things in other ways and try to motivate things by what's a reasonable or fair outcome. These fair outcomes exist often even when strong Nash equilibria or even don't exist in the game. They would like it to be that the outcome is unique and maybe predictive. That is, maybe this is what people will do. So I guess I'm going to be very much motivated and tell you in a minute what that is by the Nash bargaining solution. But there are many of these sort of different bargaining solutions. They're setting up axiomatic characterizations or sometimes game theoretic characterizations also of different outcomes that are motivated by some sort of fairness rules. They try to say that when you and I divide $1, isn't the most natural thing to do that we divide it 50-50, which will turn out to be the Nash bargaining solution. There isn't explicitly, sometimes there is a game underlying it, sometimes there isn't. Sometimes there is just this, what is called here, axiomatic characterization. But in a way, it's trying to be a reasonable predictive outcome. And this is the spirit in which I'm going to think about cooperative game theory. Even though, as I'll show you in a minute, the solution I'm using is actually a Nash equilibrium and a strong Nash equilibrium also in a corresponding natural game. Okay, so this is just a quick introduction of the the basic principles I want to use, and let me actually start with what I mean by bargaining. So the very simplest example of all of this cooperative game theory, or even thinking about these issues, comes with two people. He's, I guess, more of a pink kind of guy, sorry for the color, and a blue guy trying to divide up $100. And you can think about, so what's it mean to divide up $100? So if you want to divide it as a game theory, you can think about, maybe the simplest game is the ultimatum game. In my version of the ultimatum game, the pink guy offers $100 to the blue guy. Maybe I'm pink and Nati gets to be blue. And so I offer Nati some amount of money, and the ultimatum game would say that I can offer Nati anything I want, like $10. And if Nati accepts, I get 90, he gets 10. If Nati rejects, then we both get nothing. Okay, so the ultimatum game, I have to offer something to Nati. If I offer a big enough share to Nati for Nati to accept, then I get the remainder. Now, in a pure game theoretic characterization of the word, what do I have to offer Nati in order for him to accept? Remember, if he rejects, he gets nothing. So I think a penny. And so, again, the game is the first person make an offer, second person accepts or rejects. They both get something if the second person accepted, and both get nothing if the person doesn't accept. All I have to offer Nati in this game is a penny, so I get $100 minus a penny, and he gets a penny. This is because in a game theoretic characterization, he's supposed to be pretty simplistic in life, and he's supposed to think that if he says no, he doesn't even get the penny. Now, this is not what people do. This has been tried out in all kinds of places, in places where $100 is a lot of money, and the Nazis of the world reject the penny. In fact, they reject $10, even with places where $10 is a lot. If you don't like the game, you can think about other game theoretic characterizations. I guess here is one that is maybe more natural. What happened to my leading role here? Maybe Nati and I should simultaneously say how much money we want. Nati says a number, I say a number. If it sums to more than $100, that's too bad. But if it sums to less than $100, we get it. So that's a game too. I guess it's called a simultaneous offer-Nash game. We simultaneously say a number. If it sums to less than $100, we get the numbers we claimed. What's the outcome of that game? This game has the trouble that the outcome is not predictive. If I say any number x and Nati happens to say 100 minus x, then that's an outcome. We get our x and 100 minus x, and if we know ahead of time that that's what we're going to say, neither of us wants to deviate. Would be silly to say less than what I used to be saying, and even more silly to say more. If I say more, neither of us gets anything. So this is also a game. The trouble here is that there are all kinds of outcomes. It doesn't tell us which one is the outcome. So that's a simultaneous offer-Nash game. And in this game, it's not clear what you can do to make it more predictive. In contrast, Nash bargaining is basically trying to tell you that you're going to divide the money 50-50. And there are many, many explanations people offered for Nash bargaining, or how do you define Nash bargaining. But basically, it's motivated, but isn't the fair way to do is divide it by 50-50. And then you define fair in some way, and outcomes that, yes, indeed, 50-50 is a fair way to do it. Maybe the nicest one game theoretically is what's called the Rubinstein alternating offer game, in which I make an offer that Nati either accepts or rejects, but if Nati rejects the offer, then he gets to make an offer, and hence we alternate in this way. Now, of course, this will be an infinite game where I offer Nati a penny, and then Nati offers me a penny, and we never agree. Time is a bit worth of money, and the way this gets formalized, the delta fraction of the money vanishes between every pair of rounds. This motivates us to make more reasonable offers, and in fact, with the delta fraction, the person who gets to make the offer first gets a little bit more than half. 100 over 2 minus delta. When delta goes to 0, this goes to 50-50, and this is one of the ways the Nash bargaining solution is motivated. There are many other ones. I'm going to take this Nash bargaining solution essentially as an axiom that this is what I'm interested in. Now, Nash bargaining is a nice defined concept on two edges. What I'm interested in, what I will be interested in, what happens if you try to do Nash bargaining on a network. And again, I'm going to have one more different set of introductions of why are we doing this. So networks, there are all kinds of things happening on networks, and here actually I mean social networks. So in our friendship networks. You can think of markets, and I will tell you in a minute how to think about these markets, but maybe I want to think of social networks, that is partnership, business partnership, or friendships, and all kinds of other social interactions of some sort. There's a large theory of what's called social exchange in sociology, and the citations are all from sociology, where they're trying to understand how your well-connectedness in the social network gives you some sort of power, or gives you advantages. And I guess the basic observation is that social relations produce value in all kinds of ways, sometimes more economically clearly, and sometimes in an intangible sort of, in a friendship, whose issues are we talking about, kind of very harder to quantify kind of way. And this value is often divided unequally among the participants. And they want to try to come up with a theory of exactly how does the network tell you who is in powerful position in this network. So what they try to understand, to what extent these network imbalances are causes of the imbalances in how much power you get or how much benefit you derive from your relation has caused by the network position. So this is actually not only an old literature starting in the early 60s, but actually a very well-studied version of a branch of sociology. And one thing they did a lot of human subject experiments. And here is the basic way the human subject experiment runs. They usually get a small group of people in a room. In this particular experiment, there were 5 of them, named A, B, C, and D. And they put some number of dollars on every edge. In an example, I put $1, but they usually put higher number than that to make the players motivated. This is a network that they planned for you, if you're one of those players. And then what they want to do is get each player to engage in a free-form bargaining, usually via text exchange messages. But where the network comes in is that every player has to choose one of the edges to bargain on. So this is supposed to model that even though you might have friends, more than one friend, you like me, have 24 hours in your day, so you can't actually spend infinite time on your friends. You have to divvy up your 24-hour days between the different relations. Or maybe you have businesses to conduct and you only have so much business to conduct. But in the example, in the experiments, they have to choose a single edge and bargain in the edges. They thought that in some number of minutes a gong will sound, and if at the time of the gong, me and Nati are in agreement that we're sharing the dollar in some way, we get the money, and otherwise we don't. So this is supposed to model social power in networks, dividing attention, dividing business. But actually, you can think of this as trade also, if you prefer. And here is a very simple example to thinking of it as trade, the very same network, with the dollar divided between the edges. Here is a seller-buyer network that you can also think about just the same way. So here in our seller-buyer network, I kept the names of the edges, so hopefully you recognize that this is the very same network. I put the sellers to have a product, and for simplicity of the example, the sellers have a product of value 1 that they don't want actually, and the buyers would like to have the product and would like to buy it for something less than 1 because that's the value of the product. So what happens in a seller-buyer network is that some sellers buy the product to some buyers. So the product shifts from the sellers to buyers along some edges. This is the very same thing that happened here. The pairs agree on a matching. Just like in the seller-buyer case, the seller only has one product, so you can only sell it to one buyer. The same in the example, in the way the social experiment set up, everyone can talk to only one other guy. Same way, you're only interested in one product to buy and only half want of product to sell. Now, in the social experiments, we are dividing up $1, and actually the very same thing happens on the seller-buyer network. There are prices. The buyer E buys the product from some price P from the seller, and this is really a way to divide up the value difference between them. I guess the buyer gets the money, the seller gets the money, and the buyer gets the product for less than its value for him. So in a way, the price was just a way to dividing up the value difference between the two of them. In a way, sellers and buyers engage, at least in some place, in free-form negotiation about what the price ought to be. Very same way that the subject in these experiments engaged in free-form negotiation over what the split should be. So this is also a model of trading in networks. If you think about in trading in networks, or actually maybe you can think of it from this perspective as price setting in networks, there is actually a large set of literatures of other people thinking about how prices get set or how you can compute valid prices. And I guess I won't read the literature, but maybe want to point out this very last one, that most of this literature is thinking about how you compute one valid set of prices. Maybe all of it's about this. They're not actually trying to choose which price will happen. If there's only one buyer and one seller, that any price between 0 and 1 is valid, and they find the problem, okay, done. Not interesting. Any price is okay. But I'm most interested in trying to be something like Nash bargaining, a bit more predictive. What's the reasonable price? What prices would people agree on? Okay, so let me tell you a little bit of the results of the human subject experiments, because I think they're fascinating. So again, large literature of who did the experiments. So on a single edge, well, actually, not too surprisingly, and this I already said, with the defining Nash bargaining, that what traditionally happens is an even split. Natia and I bargain, we realize that neither of us is in a powerful position. Remember, any actual outside thing that Natia and I might know each other and maybe actually have different position is out, because it's an experiment where the subjects don't know each other. On this network, I presume you can all predict what will happen. B is obviously an incredibly powerful position. He can only trade with one of the two partners, and will trade with the one that offers him a better deal. So he's going to get almost all the power. Because you are all computer scientists rather than sociologists, I think everyone can predict what happens in this network also, though the sociologists found this actually surprising. The initial assumption was that being in a central has to be good for you, but in this guy, being in a center is not good for you. It's B and D are in a powerful position, and C is actually in a very bad position. It's getting close to nothing.
The network is known to everyone.
Actually, that's an interesting point. They ran experiments when a network was known, and they ran experiments when network is not known, doesn't matter. They figure it out. I mean, you realize you're getting good offers from the... So there's some set of experiments when the network is on the wall, so you see which point you are and who are the neighbors. And some experiments, you just know your name of your network neighbors, and you don't know who they're talking to, and it doesn't matter for the outcome. Here is actually more surprising experimental outcomes even for us. And I have to admit to you that actually they weren't running the experiments with $1. For some reason, they were running it with $24. And the only reason I can have for the 24 that it nicely divides evenly with a lot of different multipliers. So in the 24, of course, they divide the two sides by bat 12, and actually that's even that wiggle there is the bat, but probably I don't need it there. What happens on a 4-node network? This guy here. It's a bit more surprising. Oh, sorry, I started this that one better. That's less surprising. So studying in that network, which for some reason, again, the sociologists really liked, there were an awful lot of experiments run on this 4-node network, you can kind of predict it. That sender node is an incredibly powerful position, having two totally powerless neighbors. He'll extract everything. And then, once that happened, I guess you realize that two bottom guys, the center fellow there, you realize that that neighbor is utterly useless. So they divide 50-50. Well, the first one that I guess starts being more surprising is the for-long node, where but the outcome is something like this. And what's surprising here is that, well, the center nodes are in a little bit better position than the side nodes. The side nodes are totally powerless. The center nodes are in a bit powerful position, but not super powerful. If they want to exclude their neighbor to the left, they can try negotiating to the right. That's painful, actually, because then they're negotiating with a more powerful neighbor. But yet they get something from it. And I guess something similar happens on this other four-node graph, that the center node here is even more powerful position. They get even more than they get over there. In these two graphs, in fact, the two bottom graphs, every graph except what's supposedly the top, the wiggle is really necessary. There is some inherent fairness in here that my numbers are not modeling. People rarely driving the neighbor down to zero. They're giving him a penny, a small penny. So the numbers are always a bit more balanced than what I'm showing. So,
24 per edge, that's not consistent. How is the money initially distributed?
This one? 24 per edge. Every edge is worth 24.
Each person gets shared.
This is 8 plus 16 is 24. And then one in the left is 8 plus 16 is 24. That's done. That's left on the table. Because you can only negotiate with one of your neighbors. If there are multiple edges associated with a node, most of them will be left on the table, all but one of them will have to be left on the table. Okay, so the model is that you're dividing...
This one isn't divisible by 24.
Oh, oops, that one is a mistake here. I guess that number should have been something less. I'm sorry.
So that's a 6.
That's a 6 down there, and I apologize. My addition skills should improve. Okay, so let's formally define the problem just in case. So hopefully it's somewhat clear. Players bargain along the edges. To make myself a bit more general, which I will only use towards the end of the talk, the edge might have a value, maybe WUV is the value sitting on an edge. The players have to choose a matching implicitly, because everyone can only agree with one other party. So they somehow choose an edge, and that's the way they split money. So I'm going to choose a matching and some sort of allocation of goods, an outcome of this game. If M is a matching, and every matching edge splits the amount of money on the edge, and if you're not matched, you're getting nothing. This is just defining an outcome. That doesn't mean it's a reasonable outcome. The first rule of the reasonable outcome is that when it's not a matching edge, it should be the case that what two of you getting exceeds the value of the edge. Okay, this is sort of the game theoretic interpretation. This is actually a cooperative game theoretic interpretation. There's two people cooperating. If the values U and B don't exceed the value of the edge, then we should turn around and turn to each other and negotiate with each other. So say I now negotiated with someone else, Muli, and Nati negotiated with who, I don't know who. And then we turn to each other and realize that, look, Nati, we're getting hurt here because the two of us not getting enough value, as much value as the value of the edge. We could do better and turn to each other. So I'm going to call this a stable outcome. A stable outcome where every edge, the sum of the values that the two ends get is at least the value of the edge.
To assume this dynamics, you need not only assume that I know the network, but also that I know how much do you get in this iteration?
Yes. So there's a very good question here. So there's an example here of a stable outcome, just to get you a sense of what's going on at least in this particular network. The only stable value here is 1. The two neighbors have to get 0, because I said that the sum on this edge should equal, and the sum on this edge should be at least 1. That's the only way to do it, with 0 on the other side. Well, any x and 1 minus x is stable. This is actually the simultaneous offer Nash games outcome. I'm going to have to take a cooperative outcome because the deviation was that me and Nati get around and deviate somehow. These are the strong Nash equilibria. In the simultaneous move Nash game, deviations are only needed by pairs of people. As it's always with a Nash game, in order to define a Nash game, I have to say that this is a full information game in which every round we're fully aware of not only the graph, but all the offers made by everyone else. Nonetheless, remember that there are outcomes here in these graphs, in the social experiments. You don't have to tell people anything, and they're getting the right outcome. But as you see here, this isn't actually predictive. The experiments show, and not too surprisingly, that these two guys realize that they're equally powerful, and they split the dollar 50-50, and in my simultaneous offer Nash game, I'm not getting that outcome yet. Okay, so this is a Nash definition. Everyone simultaneously makes an offer. It's a Nash outcome if every pair of edges, you get at least as much money as the pair of the edge, because if that weren't true, then this pair of people would want to deviate. But I'm going to actually want to go back to this bargaining. I told you that my interest was not just in cooperative Nash games, but actually a more predictive outcome, and was thinking of extending bargaining. So remember, we had the Nash bargaining. In order to do this, I actually have to take Nash bargaining one small step further. So what is Nash bargaining one small step further? Here is a version of Nash bargaining that you'll see in a minute why it's a good idea, that each of them, they're dividing up $1, but each of them have some sort of backup in case the dollar doesn't work, in case the division doesn't work. So I don't know how to say this anymore agreeably, but one silly way to explain what I had in mind is that these are two kids dividing up $100, and I'm the pink kid here, and my mommy is kind of nice to me and will give me $5 if I fail to divide up the $100, but Nati's mommy is even nicer and will give Nati $15 if we fail to agree. So one way to put it, if they have some alternate amounts, then you would say that, well, actually, if the $100 we're giving up, we're dividing is less than the 5 plus the 15 that our mommies give us, then of course we won't be able to agree. I definitely want more than 5, and Nati wants definitely more than 15, because we both know that we have this alternate backup amount. So you can easily view that what's really going on here, that we're bargaining over the remaining 100 minus 5 minus 15, that's an $80, and that's what we're really bargaining over. So what we're going to have to do, extending the Nash bargaining game, is to divide the $80 half-half, and so I would get 45, the 40 from the division plus the 5 backup, and Nati gets 55. You get this division, for example, if you do the alternating offer Nash game, okay? Because remember, the $100 is decreasing all the time, but at the same time I have my backup and Nati has his backup. So we're not dividing the 100, we're dividing something. It's reasonable to think about that we're dividing the excess according to the bargaining game.
You're saying that experiments show that it's divided half the 80, or that that's what you expect to happen?
That would be the extension of the Nash bargaining game. I don't actually know if there are experiments for this game. I'm not sure. I'll use this in defining the what happens on networks, and that experiment shows that that's what happens. But I don't know experiments directly with this. So Cook and Yamagishi suggested about 10 years ago a solution to a model that very well predicts what happens in all these examples here, that uses this definition of Nash bargaining, and here is what the definition would want to do. It says that each matched pair will split the amount of money, or the dollar, using the Nash bargaining for pairs, where the best alternate are coming from the neighbors. So let me try to explain this to you in the prediction I made of what happens on a 4-length pass. I claimed, I guess I had 8s and 16s, but using the dollar, that he gets a third and he gets 2 thirds, and same on the other side. If you think about this outcome, you'd say, okay, let's figure out in this kind of outcome what are the alternate backup solutions each of these people has. So, for example, this player here has no alternate. He's powerless, so his alternate is 0. He gets nothing. But this guy is not completely powerless. If this negotiation breaks down, he can turn over to the other guy and, at least in a Nash sense, steal him for offering a third, or offering a bit less than a third. Because this guy's only getting 2 thirds, I can steal his attention by offering him a little bit more than what he gets right now. Roughly speaking, a third. So he has a backup for about a third, and using these as alternates, what they really did is dividing the remainder, namely 2/3, evenly, 1/3, 1/3. And every edge did this. So what Cook and Yamagishi predicted, that this kind of what they call balanced outcome is maybe that's what's happening. So again, formally defining a balanced outcome, we say that an outcome is balanced if there's a matching and it's stable, so it's a subset of this mesh outcome. But in addition, you define the best alternate value, which I defined on the network, but let me define it again more formally, that you take all the edges that this person U is engaged in, UW, that are different from its matched edge, and look at the value of the edge minus what the neighbor gets. Again, I'm using full information. I'm assuming that he will know what the neighbor is getting, and says, okay, for this much money, I could steal the neighbor W. Okay, the value of the edge is UW, he's getting gamma W, so if I offer him the difference, or offer him a bit less than the difference, then I can steal him. So the best of these options I have is my best alternative, the highest I can get if these negotiations break down. So again, the highest alternates were here. This guy has one alternate edge, this guy has no alternate edges. We said that stable, one way to put stable is that what you're getting is better than your alternate. That's another definition of stable. If you have an alternate better than what you're getting right now, you should turn to your alternate. So stable was defined that everyone has a better outcome than the best alternate. And I say a balance is if you and your neighbor somehow are halfway between your alternate options. That's the definition of balance. That as I negotiate with Nati, he's I don't know, 20 cents above his best alternate, and I should be 20 cents above his my best alternate. That is, we divided up the excess that's sitting on our edge evenly between the two of us. So that's the Cook-Yamagishi definition, and I guess what they wrote about is that all those small networks with the social experiments, it's incredibly predictive. But these are social scientists, and hence they run human subject experiments with humans in a room, so the networks were all the size that I showed you. There are many, many other networks. They actually ran networks with different weights on them. It's not always all 24. They sometimes have 8 on some of them and bigger than 24 on the others, and all kinds of different weights. But they all 4 or 5 node networks. And they didn't think about the bigger networks and even the sort of algorithmic or existence questions. This balanced outcome is a nice definition. Does it exist? Yeah.
In this even small example, it seems that the optimal solution is unique. How clear was it in an experiment?
It's not
like
clear.
90% or 50%? Or
The examples they showed, the matching is not unique actually, often not unique. If someone's very powerful, remember if you go back to that T shape on top, the matching is not unique, but the outcome tends to be unique.
Yeah, but in experiment, how clear is it in experiments?
That's unique?
No, the prediction is like within 90% in terms of the edges, not in terms of the number. It could be variations.
The numbers they're very low variation. Within 10 to 50%, they're getting the numbers that are written here. There is some follow-up work in which the sex of the participant and other things pay some effect, but within 10-15%, they're getting the numbers that this theory predicts. And yes, the numbers on all those examples, the numbers are unique. The matching is not, but the numbers are unique. Okay, so I'm going to ask, first of all, I'm going to ask the kind of question, does balanced outcome exist? And among all my questions, this is a question that even the sociologists knew the answer to. The answer is it may not. On this graph, you all see that it doesn't. It's not clear which pair could agree. The third one's going to always cheat them away. And in fact, of course, not too surprisingly, if they try experiments on this graph, which they did, it's very predictive. People will continue to negotiate and it won't stabilize and the gong will go off and they either agreed on something or they didn't, depend on the exact second the gong went off. So this they also knew. So instead we should ask, when does balanced outcome exist? When it exists, is it unique? Can we find it algorithmically? And actually, the one that the sociologists really want the answer to, what are good positions in the graph? This is why they started it. Describe what are the positions that end you with high numbers. So again, this is sort of the examples of what we want to predict. So actually, I should stop here, and I'm going to try to answer some of these questions. Hopefully, the question itself is clear. So we're looking for the balanced outcome, which was defined on slide back. One where on every single edge that negotiations ended up with a splitting of the edge, the splitting uses the Nash bargaining with the best alternate option as people's backup. So I guess what we prove, that balanced outcome exists if and only if stable outcome exists. In the triangle, even stable solutions don't exist. For example, this means that if all values are the same, the balanced outcome exists if and only if the set of nodes, which I'll come back to in a minute, which some matching avoids, form an independent set. It will be easy to see, and we'll see in a minute, that the set of nodes that can be avoided by matchings can't get anything.
A maximum matching?
A maximum matching.
Largest, not including maximum.
No, I meant largest. Maximum size matching. If a maximum size matching can avoid a node, then those people can't get anything, and there are edges in between them, then there can be a stable solution. The triangle was an example of this phenomena. Every single edge is a maximum size matching and avoids the third node, and every node can be avoided. A second corollary, that balanced outcome always exists if the graph is either bipartite or has a perfect matching. Namely, in that case, the edge nodes that are avoided by maximum size matchings are always independent. One maybe easy corollary that it's worth showing just to get started using what these things mean. The matching is, in any stable outcome, the matching has to be maximum weight. So this is not even a uniform case. Generally, it's always has to be maximum weight. So the outcomes are always socially optimal. They figure out the matching which to split to get as much money out of the system as possible. To prove this, it's only one has to use the two properties very easily. If we sum up the values of the edges that the players happen to split, they somehow split it, and that's the total value they got. Namely, every node not matched didn't get anything. If I take any other matching and sum up the values along those matching, from stability we know that the sum of the values that they get is bigger than the matching edge. And again, we know that this is less than the sum of all the values, because on another matching edge, it could be that there are nodes that got something and they're not in this other matching. So the sum of the values that we get is the weight of our matching. Weight of every other matching is bounded by the very same thing. So indeed, this is the highest weight matching. One interesting thing to note, especially after this perspective, and sort of people who think about game theory a lot, to me, this is maybe the most stunning property here, that once we know that the outcome is going to be socially optimal, we know that this edge is never to be used. Using this edge is not socially optimal. This edge has a total value of 1, but if we use it, we can't use the other two, so it's socially hurtful to use that edge. Yet somehow the solution concept is such that even though we can't use the edge, the existence of the edge affects the outcome, which is not usually true for game theoretic concepts. Yet it was true in all social experiments, that it affected people. So there is this edge here that you may not use, at least via this proof you know that no stable outcome can use this edge, yet its existence affecting the outcome you're getting. So, nice connection that I'm trying to connect this to matching theory in order to use concepts from matching theory you're familiar with. I'm going to start with the uniform weights, that is every edge has the same value 1 sitting on the edge. This is the easiest case to argue, and I'm going to start by telling you a little bit of Galois-Edmonds structure theorem. In case you're not a matching fan and maybe don't recognize these words, don't worry, and I'll tell you what they mean. So Edmonds and Galois in some early years, and I'm bad that maybe some other people are better at knowing the actual date for this, but way before our times, suggested the structuring matchings in that the set of nodes D that already came up with, all the nodes that can be unmatched with some maximum size matching, and the set of their neighbors, and then the remaining of the graph. It's easy to see that this is a good start for our characterization. So one way to think about it with the matching structure is that D are nodes that sometimes can be, sometimes can be unmatched by a maximum matching, like for example, this is a node in D. But also nodes in D are those that are reachable by even alternating paths from those nodes. For example, this node here is the length to alternating paths, namely I could swap along the even length alternating paths, get an equally big matching, and exclude the other guy instead. And obviously, this set of nodes going to have to get no value out of our system. It's obvious that this guy gets no value because he's not matched. How could he get anything? That was part of the definition. That once he gets nothing, by our stability rule, his neighbor must get the full value. Namely, if the neighbor gets something less than 1, the value with this fellow would steal him away.
You have a typo. S is D, right?
S is D.
The third.
Oh yeah, S is D. Yet another typo. I'm sorry. Indeed, this is D here. Thank you, Nati. So obviously, anyone actually not matched should get 0, because that was the definition. His neighbor should get 1. Now his neighbor's neighbor should get 0 again. For this, actually, we saw this central node. And alternating forwards, everyone reachable in an even length alternating path from an unmatched node will get 0, and everyone reachable in odd alternating length path will get 1. And indeed, these are the set of nodes that can be avoided by matching and their neighbors. This instantly has a corollary that no stable solution could exist if D is not an independent set. If there are edges between these avoidable nodes, then it can't possibly be stable. I just argued that all those nodes should get 0, and hence there couldn't be an edge there between them. So what we get here, actually thinking of our graph, the key graph that first set of social experiments we ran on, is actually a nice graph to think about this for here. The set D that can be avoided are those 2 powerless nodes on the side. A was the powerful neighbor, and indeed the solution was that he got 1 and the 2 other guys got 0. And if I take this AD part out of the graph, what I'm left with is a graph that's perfectly matchable. And I guess what I'm telling you so far, that this wasn't all that interesting. We all predicted this much. What's harder to predict is what exactly will happen on a graph that's perfectly matchable. That's where something interesting happened. That's where I had the numbers like 1/3 and 2/3 and other 1/4 and 3/4. So that's where the interesting numbers are coming in. This is actually not very surprising here. So the interesting core part is what happens if the graph is perfect matching. Remember, I also claimed that all graphs with perfect matchings have a stable solution. So I guess let me tell you what happens in a graph with perfect matching. And here I'm going to actually jump a little bit, and I'll come back in a jump and explain to you how it connects in a second. I'm going to actually think about the related problem on a partially ordered set. And if you're familiar or have done a lot of matchings and augmenting paths, maybe you can instantly guess how partially ordered sets came in. But if you can't guess, let me just define to you what is the problem I'm going to solve on partially ordered sets, and then it will take us not much time to convert it back into the matching solution. So a partially ordered set is what you see here. There are a bunch of elements. I'm going to have a single unique maximum and a unique minimum. And I guess there is this greater relation. That's an acyclic order. I'm going to think of labeling these labels on the nodes. I'm going to want to insist that the label of the maximum is 1 and the label of the minimum is 0, and the labeling obeys the partial order. That is, bigger nodes should get bigger, higher up nodes in the partial order should get bigger labels. This is what I'm going to call consistent, or I guess back in the other word we call this kind of thing stable, it turns out. what I'm going to call balanced. So here is an example of what does mean consistent. It means that a lower node gets half and a higher one should get something a little bigger, say 0.75. What I'm going to call balanced is the following definition. And I guess here also probably I should show an example. If you think of this node that I meant to be red, but maybe whatever color that is, pink, that if I look at its higher neighbors, and I take the smallest of his higher neighbors, which is 0.6, and I take the biggest of his lower neighbors, which I guess is 0.4 for him, then he should be smack exactly in the middle between his lowest upper neighbor and his highest lower neighbor. Okay? Technically, I took the maximum label value of all the nodes that are bigger than him in the partial order, and I took, the maximum label value of all the nodes that are smaller than him in the partial order, and the minimum label value of all the nodes W that are above him in the partial label, and I want him to be exactly in the middle of this. And I claim that this kind of a solution is balanced. Thinking of posets, I claim that every poset, our result is that every poset has a balanced solution, and it's actually unique. And here is a unique balanced solution on the poset that I had on the previous slide. And actually, I will need a slight generalization. If you give me a consistent labeling on any subset of the elements, I can extend it to a balanced solution, which now, of course, only will be balanced on things I didn't preset. That all the remaining elements, it will stay balanced. I won't bother with the generalization till I need it, but let me give you a quick proof or the algorithm of how you get a balanced labeling for a poset. What you need to do is find the longest chain in your poset. And what do you do on that longest chain? I'm going to pretend the longest chain is alone and balance it. And what that means, I'm going to evenly distribute the label. Remember, on the bottom, there's a 0 that's always there. And the top, there is a 1 that's always there. So between those four nodes, it divides the interval from 0 to 1 5 ways. So they get 1/5, 2/5, 3/5, and 4/5. And indeed, this is completely balanced on the chain. And I'm going to anchor my solution to this. I'm going to set this way. And look at the next chain. And what I'm going to do for chains is I look at an unlabeled chain where the average gap is as small as possible. For example, on that green chain over there, the average gap has to be, I guess, 2/5 between the two gaps. So an average gap is 1/5, and that's as small as possible on any chain. And I guess I label that one that gets, and again, distributed values evenly. And then I'm just going to repeat this. I look at this chain here, which turns out to be the smallest average gap. I guess the gap is the value 4/5 divided evenly between 3 ways, and you get some sort of numbers there. And then finally, the last one is the next smallest gap, and you get 7/10 there. And that is the unique labeling. The fact that this is actually a balanced labeling is not the key observation for noticing that this is a balanced labeling, that the gap value is going up and up and up. Every previous iteration has no smaller gap value than the previous one. I always chose the smallest gap, and if the next iteration will have a bit bigger gap, then I guess we should have chosen that one first. The fact that it's unique, it's equally easy to see. There's not much I can do on this very long chain than if evenly distribute the labels. Somewhere the gap has to be this small. So this is not so hard proof that balanced labeling exists on posets. How does that relate to graphs? I guess the easiest relates to graphs is a unique perfect matching. I take a bipartite graph is a unique perfect matching and orient its edges. Maybe matching edges down, non-matching edges up. This defines a poset on one side, namely I define it on the lower side right now, with reachability as the partial order. That is, A is bigger than B if there's a directed path from A to B. Because the matching was unique, and here I'm a little simplifying my life by taking a special case of uniqueness, this is a poset. And the observation is that the perfect matching is, this is a poset, yeah? Oh, good. And the poset labeling is balanced, and it turns out, not hard to see, that the poset labeling is balanced if and only if the graph labeling is balanced. Remember, the poset labeling is all it takes. if this guy got some sort of gamma, this fellow got 1 minus gamma. So the poset labeling contains all the information, and indeed the poset labeling is balanced if and only if the graph is balanced. So what happens with graphs that don't have a unique perfect matching, staying still with bipartite, then we have to decompose it into parts that don't have a unique perfect matching and parts that do. There's one extra issue comes in that's sort of a simple issue, that if there's an alternating cycle, that cycle is any value can be self-enforcing, that is any value x actually can come as an outcome here. And I guess maybe I want to show you as an example of what kind of thing happens here. Oops, I don't have a match. I guess yet another sort of typo. I should have matched one of those. We first take this Edmonds-Gallai decomposition that is on the left. There's 3 nodes here that are not in every can be avoided by maximum matching. A is the set of neighbors. We know that D nodes get 0 and the A nodes get 1. That leaves us with this central structure. Then I have to take a further step because I like thinking of unique perfect matchings. So I have to take the parts that are in alternating cycles and the parts that are not, or I have to take a structure of the perfectly matchable parts into what's called elementary subgraphs, which is circled here with little dots. From our previous observation, any consistent value is okay in the upper nodes, and I put in some random consistent values on the 2 different alternating cycles. And then I use my poset method to extend this to a unique solution to the remaining graph. And that's the general structure. I'm sort of out of time, but I guess I can tell you a couple more things. If the graph isn't actually bipartite, there are a few more not very hard issues come up. Remember, the solution may not exist, but I guess we overcame this trouble. The alternating cycles are a bit more complicated than they used to be in a bipartite graph. Namely, I can have an edge that crosses the alternation, and that puts bands on x. So I might say that x has to be above a half, and if I have the other crossing edge, then it should be less than a half or so. There are other alternating structures that might want to wonder about, like stuff like this. With odd cycles in them. But basically, the whole thing does extend to alternating graphs. In fact, it extends to weighted graphs. And let me finish by telling you what happens when a graph is weighted. If the existence of a stable solution can be thought of as a linear program with 2 variables for inequality. Namely, the 2 variables is the way we're splitting, and this is just for stability. And the two values should sum up to greater than the edge. This is a linear program with 2 variables for inequality. It turns out that the balancedness is, or this gap that balancedness defines, is the smallest slack from this linear program on a neighboring edge. And what we do to extend this to weighted graphs and non-bipartite graphs is follow, there's a nice simple algorithm from Oshwald and Shiloh on how to solve linear inequality systems. It's 2 variable for inequality. And I basically sort of copy or steal from the structure of that algorithm. But instead of directly using it, I always make sure to split slacks evenly along these structures that Oshwald and Shiloh applied, which indeed the structure you have seen. So I guess in summary, by the way, I guess I should go back to this nice structure here, that you get almost the same thing on non-bipartite graphs. There's the one extra restriction that, or alternating cycles that have cross edges, you either have to use a number above half or under half, or maybe actually exactly half, depending where the cross edges are sitting. But you get the rest is exactly the same. So in summary, I gave you an example of bargaining in networks. In sociology, it traditionally models social power in networks, and they're trying to understand who is in powerful position in companies and who is in powerful position in friendship graphs. But one can also think of it as a price formation in a price formation network, in a version where the players, sellers, and buyers are engaging in a free-form negotiation over the price. big goal was, and maybe that's a very good goal for me too personally, is to understand what traders are in powerful positions or what users are in powerful positions. And this Nash equilibrium or Nash bargaining-based solution is a stunningly good match to experimental outcomes. There are many general next questions here, and I only put up one that actually the sociologists are most interested in, and there are many others that I'm also interested in addition. My model assumed that the network is given. You already have friends, and you extracting value from this network given your friendship system. That's how the social experiments went. In real life, you of course are forming friends. And I'm sure a lot of our friends are formed by, I don't want to accuse anyone or myself that you form your friends by selfish reasons, but part of it, especially in company context, of course, is that kind of reason. And you're forming friends so as to get in powerful positions in networks. And that's something that one would love to model, and that's my last question on the slide. There are many other sort of, can one extend this game theoretic thinking to other contexts, which I didn't explicitly put on the slide. And thank you.